Now, first of all, if we look at the elements that are in all of these models we just looked at, which two elements are in all of these?
Carbon and oxygen. Hydrogen.
Carbon and hydrogen, exactly. Carbon and hydrogen. And so these belong to a class of compounds that we call hydrocarbons. These are called hydrocarbons. And hydrocarbons only contain the elements carbon and hydrogen. But as you can see, there's many different ways we can make compounds of just carbon and hydrogen. And if we look at this one here, here's yet another way to make a compound of carbon and hydrogen. This one has a couple different things going on. This one has what we call a ring structure in it. Sometimes we call it cyclic, like a cycle. And this here, all of you depend on compounds that have this as backbones in their molecules. This is called a benzene ring. Now, benzene by itself is a very highly carcinogenic and toxic compound. But when this gets incorporated into different molecules in the body, you'll find that this is a part of many fragrant materials. This ring is built into such things as aspirin. This is kind of the backbone of acetyl salicylic acid, which is aspirin. And a number of sex hormones and such have this benzene ring in them. And so it's a very important kind of foundation molecule for many organic molecules as well. But if we go back to these two, here's another piece another term that is from everyday vocabulary. In fact, if you hear of hydrocarbons you might hear about when we talk about gasoline or petroleum, because all your petroleum products are hydrocarbons. But the difference between these two, we say that this one here is a saturated hydrocarbon, this one here is an unsaturated hydrocarbon. So where have you heard the term saturated in your everyday vocab?
Food labels.
Food labels, and specifically what?
In fat.
In fats, exactly. In fats. And so the term saturated has to do with how the carbon atoms are attached to each other. Notice all of the carbon-to-carbon bonds in here are which type?
Singles.
Single bonds. So in a saturated fat, all of the carbon-to-carbon bonds are single bonds. Okay? And fats are huge molecules. I don't have any models of fats up here, but fat molecules have 3 different carbon chains in them that have anywhere between 12 to 18 carbons in those chains. And if it's a saturated fat, all of the carbons are joined together by carbon-to-carbon single bonds. And you'll also hear the term unsaturated when it comes to fats. Usually you don't hear the word unsaturated by itself. You'll either hear the term monounsaturated or polyunsaturated. And if it's polyunsaturated, that means it has many carbon-to-carbon double bonds present in there. If it's monounsaturated, that means it contains one carbon-to-carbon double bond. So that's where the terms come from in the fats. Now, which types of fats are more likely to be saturated? What are those sources?
So like dairy, like butter and cheese and stuff like that.
Yeah, they come from
Natural, or living things.
living things, animals specifically. Yeah, they come from animals. So animals are the primary makers of saturated fats, whereas your unsaturated fats typically come from plant sources. So you have polyunsaturated fats, which come from your corn oil, your sunflower oil, canola oil, soybean oil, and so forth. Those are your polyunsaturated oils. And then you have something like olive oil, which has a monounsaturated fat in there, and they would typically have one carbon-to-carbon double bond present. So when it comes to hydrocarbons, we also use the term saturated and unsaturated as it pertains to them. as the two main categories. And if it's a saturated hydrocarbon, that means all of the carbon-to-carbon bonds are single bonds. And if it's unsaturated, then it could either have a carbon-to-carbon double bond, like this has, or carbon-to-carbon triple bond, like this one has here. So unsaturated hydrocarbons could have carbon-to-carbon double bonds or carbon-to-carbon triple bonds. This one as well is unsaturated because it has carbon-to-carbon double bonds present in the molecule. So, next question is then, what is it that this is saturated with that this one is not saturated with?
2 more hydrogens.
Hydrogens, exactly. This one here has 2 more hydrogens than this one does here. So, if this is unsaturated, how could we saturate this? Well, what else do we need in there?
2 more hydrogens.
2 more hydrogens. We simply open up one of these bonds and we can put in
2 hydrogens.
2 more hydrogens. So we talk about a saturated hydrocarbon. A saturated hydrocarbon is one that is saturated with hydrogen. There's no way we can get any more hydrogen into here. But if we have a carbon-to-carbon double bond present, we can put in more hydrogen. Or if we have a carbon-to-carbon triple bond, we can open these up and put in more hydrogen into those places. Which then brings us to something you might read on food labels. Many times, if you eat, especially things like cookies or chips, snack foods, they will contain something called partially hydrogenated vegetable oils. Okay, they'll contain partially hydrogenated vegetable oils. And when it's partially hydrogenated, what that means is you add hydrogen to things that are unsaturated. Remember, vegetable oils, they come from plant sources, and so they're going to have some of these carbon-to-carbon double bonds. If it's polyunsaturated, it means it's going to have many of those carbon-to-carbon double bonds. So if you partially hydrogenate it, basically you get rid of many of those carbon-to-carbon double bonds that are present. Which then takes us to something else you looked at in lab last week. Now, you probably didn't call it this at the time because you built the models, but if you looked at something like this, this was your very last one in your model building exercise. You were to build isomers, and these 2 isomers are different from each other. And what is it that's different about these 2? Yeah, the location of this green one, which is chlorine. And so in this one here, you'll see that the chlorine are present on opposite sides of each other. On this one here, the chlorines are on the same side of the double bond. And this is a special type of isomers. We call them cis and trans isomers. And they're only possible whenever you have double bonds. That's because when you have double bonds present, I don't know if your lab teacher talked about this at all, when double bonds are present, what can't you do? Something that this one can do with single bonds, it can rotate or spin around. So you see, sometimes you can have these chlorines by each other, sometimes on sides opposite of each other, but when single bonds are present, there's constant rotation occurring, and it's always occurring, and there's no bonds breaking or anything. This is just what happens all the time in molecules if there's single bonds. But when we have double bonds, they're locked in these fixed positions, so you have these things that are opposite of each other. When they're locked in the sides that are opposite of each other, we call this arrangement a trans isomer, which again is found where in your everyday vocab? Trans fats, exactly. It goes right back to trans fats. It has to do with how the carbons are arranged along that double bond. This here happens to be a trans hydrocarbon, where right across this double bond you'll see that these here are on sides that are opposite of each other. If I were to switch these around, here now, what happens is that now if you look at where these pieces are, and we have the double bond, these are now on the same side of each other. That makes this a cis isomer. Well, what's kind of cool about these is with the cis isomer, notice that if I try to spin these around, and molecules are constantly spinning here, notice that with the cis isomer we can wind up having this overlap that occurs, and the molecule kind of gets bunched up. Whereas when we put it into the trans isomer, we start trying to spin these portions of the molecules around and try to have them bunch up, you'll see that as we spin them around, we can't bunch them up like we can in that cis arrangement. So in this trans arrangement then, basically those molecules get extended out very long. And it's a whole lot like a saturated hydrocarbon. A trans arrangement is a whole lot like a saturated hydrocarbon. That is this nice long chains. Well, if you remember, a saturated fat, now this is not a fat, but a saturated fat, they still have these carbon-to-carbon bonds in there with single bonds. They tend to be solids at room temperature. So when we talk about animal fats and such, those are solids at room temperature. They tend to be solids at room temperature. They tend to be solids at body temperature. With trans fats, these also tend to be solids at room temperature and solids at body temperature. The difference is that this here is something that is natural. This is things that we get out of animals. This here is something that is not natural, because basically what we've done when we partially hydrogenate a vegetable oil is we mostly get rid of all of the cis bonds, and the ones that get left behind are the trans bonds. And the reason why the cis ones go away is because they're less stable. Okay, and they're more reactive. So if they're less stable, that means they react more quickly. The trans ones are more stable and they stick around. So when you partially hydrogenate a vegetable oil, it leaves behind this trans arrangement. And again, unfortunately, your body, while we can digest these things, they're not natural, and it's more likely that the trans fats are what's causing the problems. And back in the day when I was sitting in your seat, we thought saturated fats were the real enemy. It turns out that the saturated fats are not the enemy. We're learning more and more that our ancestors way back had this natural diet that came from, we gorged on animals and we gorged on plants. Whenever food was abundant, we ate a lot. When food wasn't abundant, we didn't eat a whole lot. But saturated fats were a big part of our diets of our ancestors. So again, the term trans comes from the arrangements in the molecules and has found its way into everyday vocabulary. So what we're going to do with this here today is we're going to just kind of provide that little small foundation of these chemicals and how to name some of the simpler ones and how to draw their structures. We're not going to get too, you might still feel it's a little intense, but we're not going to get intensely deep into it. And then we'll have our exam on Tuesday of next week. When we get back on Tuesday, then we're going to get into the real meat of organic chemistry. But here's some things you need to know before we get into the tough stuff. First of all, saturated hydrocarbons. Contain two categories. They are the alkanes and the cycloalkanes. We are only going to be responsible for the alkanes in here simply because we only have 3 class periods devoted to it. If we did deal with the cycloalkanes, they would be ones that would be having a ring structure in them somewhere, which stands for cyclic, cyclo or cyclic. But we're not going to be dealing with cycloalkanes in this class. We'll start by looking at some of the simpler ones here. And if we look at the alkanes, we're going to leave a little space between them. We'll start with the simplest of the alkanes, which again is right here. And if we start with this one, we'll start by writing out its chemical formula. as CH4. Then we're going to draw out the structure for the molecule. Now, as inorganic chemists, we'd call these the Lewis diagrams, but if you're in organic chemistry, an organic chemist, you refer to these as the structural formulas. So basically, a structural formula just shows where all the atoms are located in the molecule. And then the name of this one here is methane. If we go on to the next one, and don't worry, we're not going to look at all of them. We're just going to try to learn the trend here. This one now, if we look at its formula, or its structure, we see we have the two carbon atoms joined together, and then we surround it with the hydrogens. We need to remember, of course, that carbon is always going to make 4 bonds. Hydrogen will always make 1 bond. So if we look at the formula for this, it's going to be C2H6. And the name of this one is ethane. If we go to the next one, this now has 3 carbons in it. How many hydrogens are in here? 8, yep. So then we write out the structure. And again, don't worry, we're not going to write them out for all of the alkanes. We're just going to kind of get an idea how this works. And this alkane is called propane. Now I don't have this one here, but now if we follow the trend for the next one, if we have 4 carbons, how many hydrogens is it going to have? Okay, and what is that trend we're following here?
1 carbon for every 2 hydrogens.
All right, each time we add on a carbon, we add on 2 more hydrogens. So we put together the 4 carbons, surround it here with the hydrogens. Looks like this. And the name of this one here is butane. So if you have a butane lighter or butane torch, sometimes you have a propane torch. Notice again that one of the things that all of the alkanes here have in common is that they have an A-N-E suffix. Now we could keep going on with the number of carbons and hydrogens, but there's actually a general formula here. We say that these have a general formula of CnH2n plus 2. CnH2n plus 2. Which means if we know the number of carbon atoms, the number of hydrogens is 2 times that number plus 2 more. So in the case of butane, 2 times 4 is 8 plus 2 gives us 10. So again, the number of hydrogens is 2n plus 2. So that means if we went down to octane, which has a chemical formula of C8, it'd be 18, because the number of hydrogens again is 2 times 8, which is 16, plus 2 more is going to give us 18. Well, then if we drew out all of the carbons on here, we have 1, 2, 3, 4, 5, 6, 7, 8. We then surround all of these here with the hydrogens. You see actually that it winds up getting kind of tedious and time consuming for writing all of these out. So it means we would probably like to come up with a shortcut for doing that. But first of all, let's look at the name of this. The name of this one here is called octane. This is called octane. Now, to come up with this, there's a table in your text, and you don't need to open it up to there, but if you did look in your text, you would find it on page 654. There's a table of prefixes that you'll need to memorize, and I'm going to write them down here anyhow, but again, you'll find it on 654 if you want to look. But your key to success in naming organic compounds and to know organic chemistry is your ability to count carbons in chunks. If you can't count carbons in chunks, then you will fail miserably at organic chemistry. So you must know these prefixes to succeed with organic. And so we'll count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You'll need to know the prefixes up through 10 carbon atoms. And those prefixes respectively are meth, eth, prop, bute, pent, hex, hept, oct, none, and dec. To see what we've done here for each of these alkanes, we basically put one of these prefixes and associate it with the suffix A and E. So if we wanted a 4-carbon alkane, we'd call it butane. If we wanted an 8-carbon alkane like we looked at, we would call it octane. And so, again, all of the alkanes have that suffix of A and E in there, and we simply attach these prefixes to a suffix of A and E.